All right, so let's talk our way through 2.5, number 15. So first things first, I'm supposed to determine whether this equation is exact and then solve it. So in order to execute the so-called test for exactness, what do I do?
Oh, come on, guys. Let's not do this again. Or I guess that was linear algebra yesterday when no one talked.
Yeah. It's kind of a weird mode. So yeah, it's all good. I'm good embracing the awkward silence as long as you guys are. So what am I doing, Jordan?
We should take the partial y, or we should take, the partial m over partial y, and then partial n, partial x, and they should be equal.
Good, perfect. That's the test for exactness. If these are equal, then it's exact. If they're not equal, then you can say it's not exact and you can go on with your day. Unfortunately, in engineering, what that means is that you have to find a different way to solve it. You would much rather have it be exact because that means you can solve it easily. So I guess I need a y derivative. So let's take some partials. And I'm going to give you guys a minute to work on these and remind me to start the recording again. All right, so tell me what y'all managed for derivatives here. So what did you get for m dy? I said that badly. Is this distinction known to people who haven't had a Calc 3 class from me? This little symbol that looks like a 2 but isn't, that is different than a d? Is this a known thing or no? Okay, perfect. All right, so the partial with respect to y of m gives you what? What'd you guys get?
I got x. Go ahead.
All right. X squared times e to the x squared plus y times 2x plus 3.
Like this?
Yeah.
I got 2x squared plus 3.
Always trust Karen on the algebra. That's not even algebra. Always trust Karen. All right. God, I never thought I'd say that sentence. I'm sure I'm pronouncing it wrong still. Is that right?
It's not good.
Thanks, buddy. Appreciate it. All right. So what did somebody get for the partial with respect to x of m?
Exact same.
6x squared?
No. I got x squared. The exact same as the partial of m with respect to y. I got the same.
Yeah, that's fair. Yeah, so this should be a product rule applied to these first two terms. These first two factors. This kind of second term drops off because it's just a function of y, right? So I just need to remember the product rule between these two. So first things first, that's going to be a 3x squared times e to the x squared plus y for the kind of the derivative of the first times the second. And then I'm going to have plus the first times the derivative of the second. So that's going to be e to the x squared plus y times 2x. And then, like Karen says, that algebraically rearranges to be the same as the other thing. You guys see that? Okay. So then the question is, what does that mean? So I did the test for exactness, right? I checked whether the partial with respect to y of m was equal to the partial with respect to x of n, and I got that it was. So what does that mean?
We should be integrate one of them, and then with, I don't know, respect to whatever, integrate the easiest one, and then we can find a constant with respect to the opposite variable that we integrated.
Yep, exactly. So I have my n looks like the easier one. So I'm going to say, all right, so I have a function f of x and y that should equal, well, the integral of n d, and this is where I have to think just a little bit. Which variable did we differentiate with respect to here for this guy?
We differentiated with respect to y.
Good. So even though later I differentiated with respect to x, in order to get to this point from f, this is probably a y derivative. Once I've checked that it's exact, what that means is this thing is the y derivative of a function. So I'm going to be able to integrate dy here. And that's going to be the same as the integral of m dx.
The notation will always tell us that, right? It says dy in the function.
Yep.
That term. Yeah, okay.
Yep. So this y here is going to match the idea that this is fy. And that's really just the Calc 3 chain rule. All right, so now I get to make my choice. You could integrate them both and then play mix match. When they're icky like this, I tend to prefer integrate one and then differentiate it to see the other. Just make sure you're conscious of which rung on the ladder you're on, basically. So I'm going to integrate n dy. So that's going to be my proposal. I'm going to say, all right, so f of x and y is the integral of n, which is x cubed e to the x squared plus y minus 12y squared dy. Pretty good with that? Okay, first thing is probably a pretty easy u substitution. U is x squared plus y. What's up?
I was going to say, someone's computer is like going off right now.
Yeah, it's me. My one of the admin assistants just sent me like 5 emails and a calendar invite. And my phone's sitting here on the desk, so it's getting everything done. Everything's done beeping. I hope it stops. All right. So quick u substitution. Du in this case is what?
dy.
Yep, just dy. And then the other one's just straightforward integration, right? So this guy's going to give me the integral. Oops, not the integral. What am I doing? So this integral is going to equal x cubed e to the x squared plus y. Integral of e to the stuff is just e to the stuff. And then I got minus, what do you get out of the 12y squared?
4y cubed.
Very nice. And then we have some, normally would be a constant, right? In this case, though, instead of being a constant, it is k, a function of
X.
x. Why is it of x?
Because we integrated with respect to y.
Good, because I integrated with respect to y, so there could be x. Now, if for whatever reason you were to come across one of these with 3 variables in it, that thing could be a function of 2. That makes sense? We're not going to do this in that, or we're not going to do that in this class, but it is a thing that happens.
That would be non-ordinary, right?
Yeah, good. That would be a partial differential equation. Yep.
So What would you call this kind of differential equation? Like, how would you label it?
Oh, this guy? Oh, sorry. Whoops. This thing here?
Yeah.
That's a good question. So it's not obvious right now, but this is a first order, probably nonlinear differential equation.
Okay.
The way I can tell that it's first order is I could mix and match, rearrange this into the form dy over dx equals f of x and y.
Yeah.
So I don't know that it's nonlinear. It's possible that if you did some algebra, it could be linear.
Yeah, I was gonna say, couldn't you?
Certainly, you could rearrange a linear equation to be in the form of exactness. You can actually do that with most first order differential equations. You can try to rearrange them to look exact.
Mm-hmm. So this would be in this case, it would be a nonlinear, homogeneous first order differential equation.
Remember, homogeneous doesn't mean anything unless it's modifying the word linear, or unless it's that specific linear non-homogeneous.
Okay.
So I would just call this a first order ODE without looking at it much closer, because I'd have to test for linear or non-linear here. My guess is that it's non-linear.
Okay.
I very much doubt that, in the process of subtracting this crap to the other side and then dividing by this thing, I really doubt I'm going to get the y's to come down from those exponents. Like, I think they're up there.
Just slap an ln on there, man.
Yeah, exactly. And then I'll have a y in a natural log and a natural log of my derivative, and then it'll all be real weird. All right, so at any rate here, I found this thing, and then I just want to check this against m, right? So this thing's x derivative should be that function m that I had before. So I'm going to take this thing. I'm going to think about hitting it with a partial with respect to x. I'm going to need a product rule from those first two terms, and I'm just going to grab... I'm going to get a little lazy and just grab this guy. So I need to play matching games here, right? If I differentiate with respect to x, all this stuff, well, this part goes to 0. This part accounts for those two. Right, because I'm going to have the product rule. So, you guys with me on that? The reason I know it's got to account for all of that crap is that I know it's exact, and it's got this y in the exponent, so I know none of it could be a part of this k. Because this k of x is only a function of x, so if I differentiate it, it ain't going to get any y's in it. You guys see that? So that's going to tell me that the only things that are left over is this k of x and this 4x have to match. So that's going to tell me that k prime is 4x. And so k then is what?
2x squared.
Yep, 2x squared. And then what's my answer look like?
Plug in k of x.
Okay, so I need to plug in k of x. So ultimately here, I take this guy, I plug it in there, and I get f of x and y looks like x cubed e to the x squared plus y minus 4y cubed plus 2x squared. Okay? Now what? Am I done?
No, set it equal to c.
Oh, why?
Because
Fair, because that's what you told us to do. All right, so in my original equation, they didn't ask about f, right? I invented f. I just brought that thing out and threw it in here. It didn't mean anything. I made it up. So in order to actually answer the question, I need to answer the question I was asked, not the question I made up to help. So I found f. Now the answer to the question is going to be taking f and setting it equal to a constant. So I'm going to have x cubed e to the x squared plus y minus 4y cubed plus 2x squared. And all this is supposed to equal some constant c. And that constant c is playing the thing that's going to let me plug in my initial conditions. Normally, I'd really like to get something like y as a function of x is like h of x plus a constant, right? That's where I really want to be. Why am I not going to get to that here? How would you try to solve for y by itself there?
Do some algebra, isolate the e, maybe do a little natural log and still have a y on the other side.
Yeah, that's really kind of the problem, right? I've got this y and the exponent up here. So my algebra skills let me get it down by natural logging it. But when I natural log that thing to get the y down, I'm going to end up putting this y in a natural log. And so without a great deal of cleverness, I'm not going to get this out. In fact, this one's not tractable. You're not going to solve this one. It ain't going to work. You can try, you can be super clever, it ain't going to happen. If you want to be real clever, you could try writing down the Taylor polynomial for e. And then you could kind of power these guys out. And then you could like try to factor a y out of it or something. That ain't going to work. You could try to collect all the y's and then notice that it's the Taylor polynomial of something. It's not the Taylor polynomial of anything you know, which is sad, but true. Yeah, it's kind of a disaster. The only reason I'm highlighting the idea of cramming that shit in a Taylor polynomial is that's a thing you can do to solve differential equations. We're going to talk about it for like one day in the middle of the course, but I want you to know that technique exists.
I bet that's helpful when trying to program like a calculator.
Yeah, that's actually how your calculator does things, by and large. Your calculator, it's got some. So your TI calculator has some tricks in it. That's one of those things that's kind of from back in the day when memory was sparse and programmers were cheap. Like it was cheaper to hire people than it was to put more memory into the device, which is why it's got pretty high capabilities for what it is. Like the TI calculator is as dumb as a flip phone. You guys remember what a flip phone is, right? Whereas this thing's a hell of a lot smarter than a flip phone, right? This thing has like 8 gigs of RAM. It's very fucking smart. That said, it's not real good at graphing because nobody bothered to program efficient algorithms in it because it's not a graphing calculator. And also it's got 8 gigs of RAM, so who gives a shit? Right? Like, why would you write efficient algorithms when it's cheaper to just stick twice as much RAM in the device? That's why Google...
And you could also just download the damn algorithms to do it.
Yeah, I mean, some of the time. It was actually really interesting. Last night I was chatting with a student in my machine learning class, and he was wondering why there were some rounding errors in this algorithm for calculating the determinant of a matrix. And he was using the algorithm that we like teach in linear algebra class to calculate this determinant. And the thing about it is, the algorithm we teach you in linear algebra class works on like 3x3 matrices when you're doing them by hand, and it's slow as shit, right? But it's not that slow, and it's believable that the computer could be a lot faster at it, right? The computer is a lot faster at it, but that method scales as the factorial of of the matrix that you're trying to calculate. So like if you have a... You
I
guys
don't
know
know
what
if you want to
matrix is,
stop the recording or not.
I don't. I'm interested in having this stupid Easter egg. Okay, so if you have an n by n matrix and you want to calculate the determinant of that thing, you guys know what a determinant is? I don't know how many of you are in linear algebra. Some of you? Okay. So you want to calculate a determinant of a matrix. This takes like n factorial time. The more efficient algorithm, which uses some garbage tricks, is an n cubed time. And the difference between n factorial and n cubed when n is small is not very big, right? You guys with me on that? When n gets big, this thing takes like 12 or 15 orders of magnitude longer than this one. And so it's like, sure, this is great for hand-sized stuff, but this one's the right one? So your TI calculator actually does this one if the matrix is small, because it gets exact values, and then it does this one if the matrix is big and gives you rounded values. It's a little weird. The TI calculator has a bunch of really clever shit in it because it's meant to be both precise and also fast. Does that make any sense? Okay, thank you for coming to my digression.